Hey, so you've all heard the jokes, but what we're going to do now really is rocket science. We're going to look at the thrust of a rocket engine, we're going to model rocket engine and fuel burn, and we're going to introduce you to delta V. So just click over to Wikipedia. This rocket engine article here will tell you probably more than you ever wanted to know about rocket engines. So we're going to scroll down and find what the thrust of a rocket engine is. For some reason this is an equation I remember from school, and we're going to focus just on the left-hand side of it. Basically, the force is the exhaust gas mass flow times the effective exhaust velocity. Let's not worry about the more complicated version at the moment, which takes account of the ambient atmospheric pressure. Another way of remembering this is force is mass per second times change in velocity. That would be the same if a wind was blowing on your garden fence. If the wind comes along and makes a completely 90-degree turn and goes straight upwards, then the mass per second is the mass of air per second hitting the fence, and the change in velocity is, well, all of it if it stops. So force is mass per second times change in velocity, or in the way they're putting it, it is the exhaust gas mass flow times the exhaust gas velocity. Fine. So what the hell does that mean, and how the hell do we use it in a rocket? Well, let's start coding it up. Back over in Unity, let's take a look at what we have at the moment. We have this ball. You may have a missing script. That's because it used to be a force script and it's now a rocket engine. Great, so let's start with some reasonable figures here for a start. We have a fuel mass laid out. Let's give ourselves a ton of fuel, 1,000 kilograms. If you're not sure about the units, well, we've done all that nice groundwork on units. Here you go, it's kilograms. Great. What's the next thing? Max thrust. Well, what is the maximum thrust of a rocket engine? Well, it depends on the rocket, of course. Let's have a look somewhere. Thrust. What should we use? Let's use the SSME, the Space Shuttle Main Engine. Has a maximum thrust of 2278 kilonewtons. So we are using kilonewtons, that's cool. So let's just put in 2278 in our max thrust field. Thrust percentage, I want that to be a slider, so let me show you a trick. Let's go into MonoDevelop, and where it says thrust percentage, you can use a range annotation, and we can go from 0 to 1. So 0 to 100%. If you then go back, oh, by the way, that applies to the line below, so it may be clearer to space it out like that. We're saying we want the float, thrust percent, to be available between 0 and 1 in the inspector. Here we go. Now we can ramp our thrust up. Fantastic. And we also, let's set the default thrust unit vector to 1, which is upwards. All right, it must be a unit vector or it will muck up the overall thrust. Cool, so we're going to have thrust going upwards, varying between nothing and 2278 kilonewtons, and we've got a ton of fuel. Talking about the fuel mass, that's actually, at the moment, completely separate to the mass in the rocket. So why don't we sort that out straight away? Why don't we, inside our rocket engine, say, at the beginning, in the very start, let's say that physics engine, which is a slightly funny name, we're going to rename this at some point to rigid body, but let's see how it all transpires. Physics engine dot mass plus equals fuel mass. Okay, so what we're saying is at the start, when we run the game, we're going to add however much fuel mass we've got to the mass of the rigid body. Let's try. 1001, you see, straight away. Great. Now, talking about that, how much does a shuttle weigh? Well, it turns out it weighs about 2,000 tons. So we're going to keep this in kilos for the moment. We're just going to need to get our number of zeros right. So you go 2,000 kilos and then another 3 zeros for the tons. Space it out if you want, but you can't take spaces in the inspector. So we have a 2,000 ton or 2 million kilogram dude with a ton of fuel, which is absolutely none, as you're going to see later, with a max thrust of 2278 kilonewtons, and then a thrust slider, and we want to thrust in the positive y direction. Wonderful. So we have now set up the overall parameters for the thrusting that we're going to want to do. So next we're going to want to know what the current thrust is, and we're going to want to do all of our internal calculations inside private variables and using pure SI units, i.e. newtons in this case. So we're going to want a private float current thrust, okay, and that's going to be in actual newtons, and we're going to use that for constantly keeping track of what the current thrust is. Now, what are we going to be doing in fixed updates? Well, are we just going to blindly add a force to the physics engine? No, we're going to firstly have to say if there's any fuel remaining. So how are we going to say, is there any fuel remaining? Well, if something like fuel this update, and let's imagine we had a method, if the fuel mass is greater than the fuel we're going to use this update. Remember, it's a computational thing. We're having to think ahead and say, let's work out what the fuel this update is going to be. And provided we've got enough fuel, then let's go ahead and let's just pseudocode it for now. What are we going to do? Well, we're going to reduce the fuel mass. So fuel mass equals minus equals fuel this update. Whatever that's going to be, fine. And what else are we going to do? Well, we better reduce the mass of the physics engine as well. So physics engine, struggling with my autocomplete just a little there, dot mass minus equals fuel this update. Now I know we're calling fuel this update lots of times and we could possibly create a temporary variable above, but that's as far as I'm concerned, that's absolutely fine. So how much thrust are we going to add? Well, it's not going to be that much thrust. In fact, we need to work out how much force or thrust we're going to add. Let's just imagine there's a method called exert force. In fact, you're going to be writing exert force a little bit later on. Okay, that's fantastic. So how much force are we going to be exerting? Well, we're going to be exerting the current thrust, of course, and we're going to be using that in a couple of different places. So we'll keep it there just for now. Okay. So what happens if we don't have enough fuel? Well, I'm just going to log to the console, I don't have enough fuel. So I'm just going to say else. It's probably worthy of a warning at this point. Debug.log warning, not an error, not an exception, but out of rocket fuel. Okay, fantastic. So that's the general pattern. If there's enough fuel for the coming update, then we reduce the amount of fuel by the amount we're going to use in the update. We reduce the mass of the physics engine itself by that, and then, because that's the only place that mass is taken account of in terms of the acceleration. And then if there's not enough fuel, we just log an error. All right, I'm going to do the exert force method for you, and then I'm going to challenge you to do the fuel this update. Let's make exert force slightly inconsistently void. It's just going to directly act on what it needs to act on rather than returning anything. And we can see the pros and cons of doing things this way, where we have a fuel this update that actually returns a float. The signature for fuel this update is going to be this: float, fuel this update, without the space, and that's going to be it. And it's just going to return you a number of kilograms. Yeah. All right, so that's what you're going to be filling out. But let's just look at exert force. What's that going to do? Well, it's going to say that it's going to now update this current thrust, which we declared at the top here because we need it in a couple of different places. It's going to take the current thrust, and it's going to say it's the thrust percent times the max thrust. Now, be careful. The thrust percent is dimensionless, fine. The max thrust has a dimensions of kilonewtons, or units of kilonewtons. So to get the current thrust in newtons, which is what we said we want, we're keeping everything in newtons for our actual calculation, everything in base units, then we need to go times 1,000 float. So that updates our current thrust every time we calculate exert force. If we try and build, the problem is on the else line there. Okay, let's try building. Great. So let's finish off this exert force method. So vector 3, we're going to get the thrust vector next. What is it? It's the thrust unit vector, dot normalized, because we are saying that we want to make sure that we normalize it, even if somebody gives us some weird unit vector like they come over in the inspector here, let's say, and they say thrust unit vector 10. We want to make sure this doesn't, it only takes the directional information from it, not the value of this. So thrust unit vector dot normalize times the current thrust, and this is going to be in kilonewtons again. Sorry, in newtons. This is going to be the thrust in newtons. And then finally, we're going to go physics engine.add force. We're going to register this new force in newtons of this thrust vector. So hopefully that makes sense for you. So the error I'm getting is because I've used the wrong normalize. I need to be using dot normalized like that. Perfect. So it doesn't like the fact that fuel this update doesn't return anything. Well, of course it doesn't return anything because it doesn't calculate anything yet. So you have your Wikipedia article available. Your Wikipedia article tells you f equals m.ve. You're going to need to create a couple of intermediate variables. I'm going to do that for you, but I'm not going to tell you what the dimensions are, and I'm not going to write the rest of the code for you. So let's just get you set up with fuel this update. It's going to take in nothing. It's going to have a couple of things internally. One is going to be exhaust mass flow rate, and the other is going to be effective exhaust velocity. Okay, I'm going to want you to fill in the dimensions in here for me for both of these. And then I want you to write the code below that will eventually return me a exhaust mass flow times time dot delta time, because that's the exhaust, that's the fuel this update, isn't it? And if you want a units on that, it's going to be in kilograms. Okay? And they're base units, so we can put them in square brackets like that. All right, so I want you to annotate units for the top two variables, and then I want you to write missing code in here to actually calculate what this fuel flow rate is going to be. Let me show you the challenge slide. Finally, when you've done it, I want you to burn a metric ton of fuel over in the inspector, which is how we've set things up. And I want you to make sure that the delta V is 2.23 meters per second. What that means is that once you've set up your fuel mass here as 1,000, your max thrust, etc., and your mass, when you actually pull up the thrust, it doesn't matter what thrust you use as it happens, but when your fuel is expired, you want to see a velocity vector of 2.23 meters per second. Cool, good luck. Go ahead and try and fill in those few lines of code that actually calculate the fuel burn now. Okay, welcome back. Let's get this fuel burn calculation on the road, shall we? So, exhaust mass flow. Let's just build, see if I've got any problems. No, it just doesn't like the unassigned variable. That's fine because we haven't used it yet. Okay, cool. So, effective exhaust velocity. What is it going to be? Well, if you look on the Wikipedia article, you will see that it's 4462 float, and that's in meters per square second, meters per second, for a liquid hydrogen oxygen engine. Let's just take a look at that. Here it is, right in front of your face. 4462 meters per second for a liquid hydrogen oxygen engine, and that is the effective exhaust velocity. Awesome. So that is a great starting point. What next? So once we know the effective exhaust velocity, we need to think about working out what the actual equation is. Well, let's write down what they said. They said that thrust equals mass flow, in simple terms, times exhaust velocity, right? And we want to know what the mass flow is. So rearrange the equation, and it equals thrust divided by exhaust velocity. Fine. So exhaust mass flow is the current thrust in newtons, try to be careful to use newtons, divided by the effective exhaust velocity, right? And that's it. That's all you actually have to do. You just have to say what the effective exhaust velocity is, and then say that the current thrust divided by that exhaust velocity is equal to the exhaust mass flow, and then do the times delta time, and you're off. Let's try it. Let's come over to Unity and burn 1 ton of fuel. You ready? I'm going to start with no thrust. I'm going to play the simulation. I'm going to ramp it up. Look how quickly this ton of fuel's going. Boom! Disappeared, leaving 8 kilos of fuel in, 2.23 meters per second of delta V of change in velocity, and now the thing is just coasting away in space on its own with no more rocket fuel left. Lost forever, like Sandra Bullock in whatever that film was, Gravity. Let's try it again at a lower thrust percentage. Let's try starting at about 50% thrust. Now the fuel will be consumed slower, take twice as long to consume it, but you'll notice when we look at the physics engine that the final delta V is the same. It doesn't matter how fast you burn your fuel, you're going to still end up with the same amount of change in speed. A lot of space flight is to do with this delta V budget. It's to do with how much fuel you have, and hence how much change in speed you can achieve with that fuel. Let's just test one more thing. I want to make sure that our normalizing our unit vector has worked. If some monkey comes in here and puts 1, 2, 3 for our unit vector, then it should make no difference because we normalize it and we take it down to 1. It doesn't make any difference. Great. So I'm going to leave it at 1 just not to so I'm not being awkward. And that's it. You have a variable thrust rocket engine. You can also notice that the mass, if we, for instance, burn very slowly, watch this. At the start, the mass is added to the mass of the rocket, and there's lots of different ways of doing this. And then as the burn happens, the excess mass over 2 million kilos is exactly the fuel mass. It all drops. The acceleration, by the way, is changing, of course, all the time. You would see that if you made the mass of the rocket maybe 2,000, and then you made the fuel mass 1,000. Watch this burn now. See, I'm going to turn the thrust right down. This is a significant portion of the mass of the rocket now. So the net force is fixed. But what you'll find is the acceleration of the rocket is increasing all the time. We're not seeing the acceleration here, but the acceleration will be increasing because the mass is dropping and dropping. Let's make that really clear by making the rocket only have 1 unit of mass. Turn the thrusters right down and then burn again. Watch the speed the velocity vector goes up. 100, 200, 300, 400, 500, 600, 700, 800, 900. You see it's getting faster and faster and faster and faster and faster. It's accelerating at a higher and higher and higher rate because even though the force is constant, the mass is dropping all the time. Okay, I hope that's clear. Really powerful general rocket engine you've got there. Plenty of other ways you could architecture it, but this is good enough for now, and congratulations.